So let's start by designing an emitter follower. So an emitter follower is basically like the simplest thing that you can do with transistors in terms of linear design. It's basically a buffer. It's going to get a high impedance input, and it's going to turn it into low impedance output. This is going to be used as the output stage of the amplifier, and you will see these kinds of circuits anywhere when you need to drive a low impedance load. Okay, so before we start, the most important thing when you're designing an emitter follower is knowing your load. So in our case, just to make the calculations easier, since this is just going to be an example, we're not going to be actually designing the output stage of the headphone amplifier here. It's just going to be an example so that we get there. Our load, so the value of the resistor, it's going to be 100 ohms, just so we can get some simpler calculations. This would be, for example, our headphone. Also, the second thing that you need to know is your input source. So what's going to be your input source? In an emitter follower, you basically have unity gain. So whatever you have in the input, you get in the output. It's just a buffer. In reality, you get less than unity, but for practical purposes, you don't have to care about that. So just think that if you get 1 volt in, you get 1 volt out. That's it. So again, to make the calculations easier, let's say that our input signal, here, our Vin is going to be 1 volt peak to peak, just like the output of the headphone output of a smartphone that we looked at before. So let's just draw this here. It's just so that we are on the same page. So it will be a signal kind of like this. This is a horrible sine wave, but okay. So it's going to be 1 volt peak to peak. So from peak to peak, you have 1 volt, and the V peak is going to be 0.5 volts because you have plus 500 millivolts minus 500 millivolts. Now what we have to calculate is the current that will be flowing in our load. So in this case, it's very simple. The current is going to basically be plus 0.5 of a milliamp and minus 0.5 milliamp. Okay, so it's very simple. It's just Ohm's law. You just get the voltage, the peak voltage, divided by your load, and you get the load current. So in this case, I load is going to be 0.5 milliamps. Okay, so very simple. Again, I've chosen this just as a way to make the calculations a lot easier. Okay, so after you have these variables, then you can start designing your emitter follower. So let's do this. The emitter follower basically looks like this. So you have V plus here. This goes into an NPN transistor. We're going to be using NPN here, just so that it's a lot simpler to learn. Later on, we will be using PNPs for this stage of the amplifier, but when we get there, we'll learn more about them. So you always have a meter resistor like this. It's an RE. So you have an RE here. This is going to be the resistor layer. Is going to determine our output current. Since this is an audio application, it has to be AC coupled. We don't care about the DC value. If this was going to be like a DC coupled, if you had, like, for example, like split supplies or something like that, then you would tap it off like from here and go to the load directly. This is going to be AC coupled since it's a single supply, so it has to go through a capacitor to our load, okay? This is going to actually be our load. The headphones, for example, they're going to be 100 ohms here, just so we know. We're going to have a 1 volt peak-to-peak signal. Okay. And now that we have in mind the load, the output voltage, and our current, there is a rule of thumb whenever you are dealing with Class A topologies like this. This is a Class A topology, because this device is always going to be conducting, even if there is just no signal in the input. That means that the rule of thumb is that whatever your output current has to be, you always need to have double the current here. So in Class A, you usually have 2 times the output current going through this, which is basically going to be a current source. Okay. So since we are going to have half a milliamp here, that means we must have at least 1 milliamp flowing through this. Just so that we're going to be playing on the safe side here, let's say that we're going to have 2 milliamps flowing through here. Okay, so we're going to have 2 milliamps. Okay, just so that we're on the safe side, and again makes calculations easier and stuff like that. Okay, so we know that we'll always have 2 milliamps flowing through here, so that we can satisfy our plus and minus 0.5 milliamps through our load. From this point on, we can start looking at RE. So to calculate RE, it's very simple. We're just going to be using Ohm's law. So we need to have 2 milliamps flowing through RE, since the collector current is going to be the same as the emitter current. So for that, we need to keep in mind 2 things. The voltage swing that we'll have here will be the same as the input voltage. So we are going to have 1 volt peak to peak appearing here. So we need to have at least some voltage here above that 1 volt peak to peak, so that this device is always conducting and it's always in its linear region, and it never goes off. Okay, so we need to take 2 things into consideration. First of all, we have our, let me just draw this here, okay, the base. So first of all, we have VBE here, which is like that usual like diode drop that you get on BJT devices like this. So in this case, for this device, let me get the data sheet in here, we see that VBE is 660 millivolts. So let's just write that down for completeness sake. So our VBE is going to be 660 millivolts. Okay. And this is going to determine the lowest voltage that we can have here in the base of the device, because we need to have at least VBE here to get this device to conduct. Of course, there are variations in VBE, so you always need to get to put a voltage here that is above VBE, just so that you can take care of all those variations. Another thing that you got to keep in mind is the saturation voltage, or you have here VCE sat, which is the saturation between the collector and the emitter. Because you can drive this base above your power supply, because since this is going to be, later we're going to put the rest of the circuit here, but this is going to be AC coupled. So if you had, for example, the full V plus here, when this swing of 0.5 volts appears in the input, it would drive it 0.5 volts above the supply voltage. And that would be a problem because we have VCE sat, which is just the voltage across the device. In case of this device, we can't exceed 90 millivolts. So that's going to clip the signal at the plus side. Whenever you're looking at the data sheet, you always have to keep in mind that the VC sat, it's always given at different currents, because the higher the current, the higher your VC sat is going to be. In this one, they have put them for 10 milliamps and 100 milliamps. In this case, we're not going to be using it for higher current, so we're not going to be drawing like 100 milliamps from this. But when we get to the actual output state, we'll be drawing like around 100. So then when we get there, we'll have to use another value. But for this, they quote at 10 milliamps, 90 millivolts. Okay, so you got to keep it in mind. So let me just write this here. VCE sat is going to be 90 millivolts. So right off the bat, we know that our voltage swing here, our voltage here can't go above V plus minus 90 millivolts, but it's never going to go there because we have basically what, like a 1 volt peak to peak signal here, so it's small, it's very small. The second thing is, since our signal is going to be 1 volt peak to peak, and 1 volt peak to peak is going to be appearing here, we need to design this so that the voltage here produces the current that we need, which is the 2 milliamps, but that voltage is also higher than our lowest peak. In this case, our lowest peak is going to be minus 0.5 volts, so we need to have at least 0.5 volts here. Again, you always need margin, always put a little bit more voltage. So you need a voltage that's greater than 0.5 volts here, which means here we are probably going to have something like something greater than 1.2 volts. Okay, because then we get the diode drop here, and then up here appears only 0.6. So let's think about that. In order to get 2 milliamps flowing through RE with, for example, let's say 1 volt here, we'll need RE to be 500 ohms, because it's just basically Ohm's law. You can get through there by the current. Just for example, if we have 1 volt here, so 1 volt here, that means that 1 volt divided by 2 milliamps, it's 200 ohms. So then we've discovered RE, so 200 ohms. Oh, sorry, 500 ohms for 2 milliamps. Okay. If this voltage was higher, for example, was like let's say 2 volts peak to peak, then you would have to choose a higher voltage here, let's say like 1.5 volts, just so that you can take care of that bottom side of the sine wave. So in this case, we're going to use 1 volt here. No, not the problem. Later on, we're going to be looking at like current sinks. Then you can maximize the swing in this output stage by putting this this node at half of the usable voltage range that you have, but that's we're going to look in the in a later part of the video. So we know that we need to get 1 volt here, so that means that we need to have around like 1.66 volts in the base at all times in order to keep this device on, all the currents flowing, and everything happy. So how do we do that? We do that using a voltage divider. Okay, so voltage divider time. Simple stuff. Okay, and we decouple our input signal in here. We put this capacitor here just so that any DC that might be in this input signal doesn't upset the biasing that we've set for this device. So let's call this like R1, R2. So we need to make sure that this voltage divider can provide, first of all, the current required to keep this transistor on. That's very simple to calculate. You just need to go to the datasheet and you see, for example, the HFE. Let's say that it's 100. For this one, since we are going to be drawing 2 milliamps from here, you need at least 2 microamps in the input here. That's like almost 0. So then basically, as long as you're not going in the like hundreds of Ks of ohms here, you were okay. It's going to be enough for this device. So we're okay. We need to get at least like 1.66 volts here. So here in my calculator, I just wrote like a little program that lets me calculate voltage dividers. This is so that I just don't have to memorize the formula, like all the permutations of the formula. So this is very simple. So let's just say that we have like a voltage input of 12 volts. We want 1.66 volts out. And just so we have something to work with, let's say we want like 10K for R2. So we calculate R1 and it gives us like 62.3K. This is not a standard value, so let's go to the nearest standard value that we have, which is 68K. Let's calculate R2, around 11K. So the nearest value is 12K. So let's calculate the out. The out is going to be 1.8 volts. Good enough. That means that no matter the variation that we have here in the VBE, this will always be biased to at least 1 volt. In the case if it is like 1.6, 1.7, it means that we will have like around 100 millivolts more in this node, so it's going to pass 2.2 milliamps, but hey, that's all just margin. It's the real world. We're not doing any like theoretical stuff here, so that's good enough. So we'll have 1.8 volts here at the base, around 1.2 volts here. So it all works out in the end. So let's just write this out. 68K. And here you'll have 12K. Okay? So, and our current is going to be like less than a milliamp. So now we've determined all of the resistors in our emitter follower. The only thing left to do is to determine these capacitors. So these capacitors, they are pretty simple to calculate. If you simplify, like for example, this portion right here, this is just a high-pass filter. So you need to make sure that this capacitor is big enough that when it's in series with this resistor right here, your load, it doesn't cut the low frequencies that you're interested in. And the low frequencies that you're interested in case of a headphone amplifier, it should be like 20 hertz. You should have like almost no attenuation at 20 hertz, just so that you can have the full spectrum. But depending on what you're building, if you're building like, for example, something for a tweeter or like a mid-range or something like that, you can make this capacitor smaller just because you don't need that low of a frequency. To calculate this is very simple. What I recommend, you just go into like, for example, LT-Spice, and you just play around with this, because LT-Spice will give you nice graphs and stuff like that. Don't mess around with the, I think it's 1 over 2 pi RC. Yeah, I think it's 1 over 2 pi RC or something like that, which is like just the formula for the 3 dB cutoff. You don't want to have, like, for example, your 20 hertz at minus 3 dB, because that's like half of your input. What you want is to have the least amount of attenuation possible. I always strive for less than 1 dB of attenuation at 20 hertz. It's better to have, like, the less attenuation you can get with along with it, the better. So just plug it into LT Spice, plug it into something, and you get like this capacitor. Okay. If you want to calculate this by hand, I can then later just do a video showing how how LT Spice and all those online calculators that you get actually give you those graphs. And it's a very good way to learn complex numbers, is to do stuff like this, to calculate filters. So now for this capacitor, this is also going to be a high-pass filter, but this high-pass filter is going to have these two resistances in parallel. So if you want to calculate this, it's very simple. You do the same thing that you did to discover the capacitor here, but you put these two resistors in parallel. Okay, and then you get the high-pass filter that you want. In this case, like my program, it already calculates it for us. The output impedance of this is going to be 10,200 ohms. Let's see if I can focus on that. Here we go. So yeah, here. Yeah, that's it. So you can just calculate it, plug it into the unknown calculator or LT Spice. You want to calculate this capacitor with a series resistance of 10,200 ohms, just like you did for here. There it is. Like, this is very simple. There's not much to this. So now let's take a look at a different configuration for this transistor, which is very simple, because with this transistor, for these low currents, it's not a problem. With one transistor, you get enough current, enough gain, enough HFE here, so that your input impedance here is relatively high. But if you're going to be driving, for example, a 16 ohm load, and you're going to be putting, like, for example, 1 volt peak to peak through it, then you start drawing a lot of current, and this base starts requiring a lot of current through it, which makes this resistive divider, makes it have like a lower input impedance, and then you just get into a lot of trouble. Remembering that when you go to create amplifiers, the output of the amplifiers usually high impedance. So you need like a high impedance here, and you can do that using a different transistor configuration. So let's take a look at that right now.